Hello and welcome to this video lecture on estimation theory. In the last few videos we gave an introduction to probability theory. We defined probability spaces, talked about discrete and continuous random variables, we talked about their density functions, defined the expectation and variance operators, the normal distribution in one and several dimensions. We introduced marginal distributions and discussed quite a bit about conditioning. In this part, we will state Bayes' theorem, and we will talk about estimation theory, estimators, and we will present the minimum variance estimator. So let's start with the celebrated Bayes' theorem. We have defined the conditional probability of A given B as the quotient of the probability of their intersection, the intersection of A and B, over the probability of B. Of course, provided that B has a non-zero probability. Likewise, we can define the probability of B given A as the probability of the intersection over the probability of A. We can combine these two equations to obtain Bayes' theorem. Bayes' theorem states that the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. It's a very simple formula, and that's the proof, but it turns out to be one of the most important results in all probability and statistics. Before we proceed, we need one more result, the law of total probability. This is again a very simple fact about probabilities. We have already shown that for an event A and the partition of the sample space into a sequence of disjoint events Bn, it holds that the probability of A is the sum of the probabilities of A intersection with Bn. Here, without loss of generality, we will assume that the probability of all those Bn is not equal to 0, and we will use the fact that the probability of A intersection Bn is equal to the conditional probability of A given Bn times the probability of Bn. If we plug in this formula into the above equation, we have that the probability of A is written as the sum of the conditional probabilities A given Bn times the probability of Bn. This is known as the law of total probability. As an example, an easy way to partition omega, the sample space omega, is to take an event B and its complement. B and its complement form a partition of omega. Then, according to the law of total probability, P of A, the probability of A, is given by this formula. This is useful when we don't know the probability of A, but we know such conditional probabilities, and this will be often the case when using Bayes' theorem in applications. Let us combine Bayes' theorem with the law of total probability to interpret the results of a COVID test. Be warned that all data shown here are just made up for the sake of understanding Bayes' theorem. A certain test for COVID has sensitivity 99%. This means that if a person has COVID, the probability that the test will reveal it, the probability that the test will be positive, is 99%. The test has a specificity of 98%. This means that the probability of the test being negative, given that the person is healthy, is 98%. The prevalence of COVID in the general population is 10%. Now, before we do the test, what is our belief about whether we have COVID? Suppose we have no other evidence to suggest we do have. Our belief is that 0.1. This is the prior belief. It is the probability we have COVID if we have no other evidence to suggest that either that we have or that we don't. What is now the probability that we do the test and it turns out to be positive? That's a different question compared to whether we have COVID. By the law of total probability, the probability that the test gives a positive result is equal to the probability that it's positive given that we have COVID times the probability that we have COVID plus the probability it is positive given that we're healthy times the probability that we are healthy. The probability that the test is positive while we're healthy is equal to 1 minus the probability that the test is negative while we're healthy, given that we're healthy. This is simply because the event negative is the complement of the event positive. What is the probability we are healthy? It is 1 minus the probability we have COVID. And now if we plug in all the data provided above, we can see that the probability that we test positive is 0.117, which means 11.7%. What is now the probability that we have COVID given that we have tested positive? Using Bayes' theorem, this is equal to the probability we test positive given we have COVID, which is known, times the probability we have COVID, which is again provided, it's known, divided by the probability we test positive. And if we plug in all the data from above, we will find that the probability we have COVID given that we test positive is 84.6%. It is interesting to observe a change in our belief in this example. Before we did the test, the probability of having COVID we said was 10%. After doing the test, we see that this belief changes. We use the evidence to tell now that we are 84.6% certain that we have COVID. Let's have a look at some terminology. The probability that we have COVID without any additional evidence is called the prior belief. The probability we have COVID given that we test positive is called the posterior. It is the belief we have after we obtain some evidence. And the probability that we test positive given that we have COVID is called the likelihood. Bayes' theorem is also applicable when we have continuous random variables. So let x and y be two real valued and continuous random variables. This means they have some density functions. The probability of x given y is known to be the probability of x and y, divided by the marginal. So once again, the conditional is equal to the joint divided by the marginal of y. Of course, provided that the density of y is not equal to 0. And similarly, we can write the same for y given x. So the density function of y given x is equal to the joint divided by the marginal of x this time, the probability of x. And by combining the two equations, so we work along the lines of the first proof of Bayes' theorem for probabilities. Here we are doing the same for densities. We have that the conditional of x given y is equal to the conditional of y given x times the density of x divided by the density of y. Just keep in mind that the marginal probability density function of y, py, is given by the integral of the joint dx, the integral with respect to x. And the joint, of course, can be written as the conditional y given x times px. That's a useful formula we use sometimes in practice. So py is equal to the integral of py given x times the marginal distribution of x dx. Let's have a look at an example. Suppose that x and n uppercase are independent real valued normally distributed random variables with mean equal to 0 and variances sigma x squared and sigma n squared respectively. And suppose that y is their sum. We measure y, we measure the sum of two random variables. And from the sum, we want to understand whatever we can about x. So we need first of all to determine the density function of x given y. By Bayes' theorem, we can simply use the formula and we can say that the density of x given y is equal to the density of y given x times the density of x divided by the density of y. And we can focus now on the denominator, the density of y, and we can use the formula we mentioned before, and we can write it as the integral from minus infinity to plus infinity of the conditional density of y given x times the density of x dx. And afterwards we can observe that y is x plus n. So instead of y, let's just go on and write x plus n, and let's replace the value y lowercase by x plus n lowercase. I will leave it to you as an exercise to show that the density of x plus n given x is equal to the density of n evaluated at y minus x. That is a very important exercise, and we will be using it in the context of the Kalman filter as well. So now, using this formula, we can plug it back in, and we have that the density of x given y can be written as the density of n evaluated at y minus x times the density of x divided by the integral from minus infinity to plus infinity of the exact same quantity as in the numerator dx. Just a reminder, we have that n follows the normal distribution with mean 0 and variance sigma n squared. This means that the density function of n is given by this expression over here, 1 over sigma n times the square root of 2 pi times this exponential, in which we have n squared there. So if we plug in that density function into the above expression, we have this lengthy expression over here. And a few cups of coffee later, if you take the pains to do all the derivations here, you can find a nice closed form expression, and you can determine the value of that integral from minus infinity to plus infinity, and you will find that the density of x conditional on y is given by this expression. So if you know y, if you know the value of y, of the random variable y, you can have the density of x. And this way we have estimated x given y. This is our first estimation exercise. And in fact, we have estimated not just one value for x, we have estimated the whole distribution of x given y. The conditional random variable x, given that y is equal to y, is normally distributed, and the mean is given by this quantity here. And we also have the variance of x given y. Now let's give an example to see how this works. Suppose that x is a normal random variable with mean equal to 2 and variance 0.3, n has a mean of 3, variance 0.15, and then of course y will have a mean of 5 and variance 0.45. Suppose we obtain a measurement from y, and this is, suppose it happens that it's exactly equal to 5, then the expected value of x given that y will be exactly equal to 2. As the measurement goes away from the mean, likewise the estimate we have for x will move away from its mean value as well. But not only do we have the expected value of x given y, we have the whole distribution of x given y. And what you see here with the dashed line is the probability density function of x given y for a value of y equal to 5.16 in this example. So that's all for now. Please have a look at the slides and the handout where you can find some exercises you can solve. In the next video lecture, we will talk about minimum variance estimation. Until next time, goodbye.